Yeah. So good evening, everyone. So today we will discuss a few questions from digital electronics as well as signals and systems from previous year gate questions. So last class we have discussed some questions on Laplace transform, jet transform, and also on the ROC criteria. These things we have discussed, and also we have seen some questions on state diagrams also. So now we will see this question. This question was given in GATE 2015 ECE set 2 for 2 marks. So you can read the question. The question reads as follows. The figure shows a binary counter with synchronous clear inputs. Okay. With the decoding logic shown, the counter works as does. So they have said there is a counter it is given and Q0 to Q3 are the outputs of the counter, binary counter, and the outputs are connected to through some XOR gate to the clear input, and there is some clock it is given. So we need to comment on this whether what is the modulus of the counter. So first of all, let us discuss something about counters. Then uh, we will come back to this question. Yeah, we will see about counters. So the counter is a digital circuit which counts the number of clock pulses arriving at the clock input. So basically, counter is a sequential circuit. Okay, it is a sequential circuit. Okay, uh, which counts the number of clock pulses arriving at the clock input. Okay, and let us say fine these number of clock pulses arriving at the clock input, uh, that the actually okay, let me talk about the different counters. Actually we have two types of counters. One is the actual counters, and another is the applications of shift register. You might have studied about shift registers. So applications of shift register, we have one of the application of shift register. One of the applications of shift register is counters, but these are not actual counter, but still they are called counters. This I think mostly you might have studied ring counter and Johnson counter. And Johnson counter. So actually these are shift registers. If you like connect the shift register in such a way, then they'll work as some kind of counter. They're called ring counter and Johnson counter. And actual counters we have. So actual counters are, we can again classify into two. One is asynchronous counter, asynchronous counters, and synchronous counters. Synchronous counters. So actual counters we have two. One is asynchronous counters and synchronous counters. So in asynchronous counters, so to have some asynchronous counter, one is we can use any type of flip flop which should be in toggle mode. So we can use any type of flip-flop which is in toggle mode. You know, right, what is toggle mode? Let us say for a flip-flop, let us say some flip-flop we have. Let us say T flip-flop or JK flip-flop, Q or Q bar are the outputs and state are outputs. Clock are applying. When T equal to 1 we apply. When every clock pulse, let us say it is edge triggered flip-flop. So for every clock pulse, the output should toggle. That means whenever the previous state was 0, then it should go to 1 at the application of clock pulse. And whenever the previous state is 1, it should go to 0. So between 1 and 0, the output should oscillate. So that is toggle mode. You know, J-K flip-flop also we can operate in toggle mode when J and K both are ones. And also SR flip-flop also we can use in toggle mode. Sorry, we cannot use. So asynchronous counter, we need flip-flops that should be in toggle mode. For synchronous counter, any flip-flop we can use. Any flip-flop we can use. Okay, to construct counters, we need flip-flops and some combination circuit, some gates will require. And in asynchronous counter, the clock pulse, let us say in asynchronous counter, we have three counters, let us say, sorry, three flip-flops. Then the clock pulse is given only for the first flip-flop, and the output of one flip-flop drives the clock input of the next flip-flop. Let us see in some 3-bit asynchronous counter. 3-bit asynchronous counter means it will have three number of flip-flops. Okay, 3-bit asynchronous counter, three number of flip-flops. Let us say some J and K inputs and Q and Q bar outputs. Flip-flop 1, flip-flop 2 and flip-flop 3. Now for only the first flip-flop, directly the clock pulse is given. Okay, and output of one flip-flop will be connected to the clock input of the next flip-flop, like this. So output of this flip-flop will be connected to the clock input of the next flip-flop. Okay, so this is main difference between synchronous and asynchronous counter. So for the first flip-flop only we give the clock, and for the rest of the flip-flops, the output of Q or Q bar output of the previous flip-flop will drive the next flip-flop. I think these things anyway you have studied, just I'm revising. And in synchronous counter, for all the flip-flops, let us say 3-bit synchronous counter, let us say we are using three flip-flops, some J, K, this is clock input, J, K, clock input. For all the flip-flops, simultaneously the clock pulse is given. That means let us say we have clock input this one. Let's say this is clock. Then for all the flip-flops, simultaneously the clock pulse is applied. This is synchronous counter. Okay, that's the main difference. For all the flip-flops, same time clock is given. For asynchronous counter, output of one flip-flops drives the clock input of next flip-flop. And for constructing asynchronous counter, we require flip-flops which are in toggle mode. And any type of flip-flop we can use for constructing synchronous counter. Okay, and as I said, the input to the counter is nothing. Actually, external input is nothing but only the clock is the input. Some counter, only clock is the input, and the states are nothing but the output. Let us say 4-bit counter, then you will have some states Q0, Q1, Q2, Q3. So based on the binary values of this, we will decide the state of the counters. Okay. Okay, and as I said, an n-bit counter requires n flip-flops. flip-flops. N-bit counter requires n flip-flops, and an n-bit counter can count from 0 to 2 power n minus 1. Okay, an n-bit counter can count from state 0 to 2 power n minus 1. Let us say if n equal to 3, then it's a 3-bit counter. It can count from 0, 1, 2 up to 7, then again go back to 0 like this. 0, 1, 2, 6, 7 like that it will counts. Okay, and for this, let us say it is counting this, then the modulus of the counter is this one. So the modulus of the counter is how many number of states that it can count. That is nothing but the modulus of the counter. Okay, so for this, how many states it can count? Let us say 3 states it can count. So it is a mod. How many states it can count? 8 states. It's a mod 8 counter. Okay. Give me a second. Okay. So if it is a mod n count, let us say mod 8 counter means it can count from 0 to 8 minus 1. Okay. Let us say a mod n counter means it can count states from 0, 1, 2 up to n minus 1. It can count. How many states it can count? That is nothing but modulus n counter. Okay. So that is about counters. I mean some introduction about counter, and also you should know like how to design counters. Also, you know, hope you know that, but I'm not touching those details. Uh, this is some introduction about counters. If you have any doubts, you can ask, or if you want me to explain further in this, you can ask, or else we can solve that problem. Pardon? Okay. Yeah, why toggle mode means see, let us say 3-bit asynchronous counter I'm taking. That means 3 flip-flops we require in toggle mode. Okay. Then only the states will change. Let us say JK flip-flops I'm using. 1, J and K1, then only it will be in toggle mode. So this J and K are connected to ones. Now for the first flip-flop, let us say negative edge triggered flip-flop, something I'm taking. Clock is connected here. For the first flip-flop, let's say QQ bar. And now Q output of one thing is connected to the clock input of the next one. This is the second flip-flop. Now let us say this is third flip-flop, Q and Q bar. Now these are the outputs. Let us say this is Q1, Q2 and Q3 are the final outputs at state of the counter. Okay. Now, how the states will change means if they are in not toggle mode, we won't get the state change. Let us see that. Let's say this is Q1, Q2, and Q3, right? Now, can somebody tell me when for the first flip flop, when the output of the flip flop toggles, since J and K both are ones, so when the negative edge of the clock occurs, then only the output toggles, right, for the first flip flop, right? That means for every clock pulse at the negative edge of the clock, the output of first flip flop will toggle, that is Q1 will toggle. And what about for the second flip flop? For the second flip flop, when it toggles, so output of second flip flop Q2 toggles when Q1 is changing from high to low, right? Since these are negative edge triggered flip flops, at the negative edge of the clock or clock input, the output will toggle, right? When Q1 is changing from high to low, then the second flip flop output will toggle. Similarly, when Q3 toggles, when Q2 is changing from high to low. And Q1 toggles, as I said, Q1 toggles when clock is changing from high to low, when clock is changing from high to low. Now let us say Q1, Q2, Q3 are the states. Initially, let us say the outputs of all the flip flops are 0, 0, 0. None of the clock pulses are applied. Let us say we have applied the first clock pulse. When first clock pulse is applied, what will happen? For every clock pulse at the negative edge of the clock pulse, the first flip flop toggles, right? Let us say like this, we apply the clock, right? Let us say this is the clock. At the negative edge of every clock pulse, this we are applying at the clock input. The first flip flop will toggle. That means when initially 0, 0, 0, that is the starting state, first clock pulse is applied, then what will happen? Q1 toggles, that Q1 becomes 1. And what about Q2? When Q2 toggles, Q2 toggles when Q1 changes from high to low. When it is changing from 1 to 0, then only Q2 toggles. Since Q1 is changing from 0 to 1, it will not toggle. Q2 will not change, right? Only negative edge it will changes. So it will not toggle as it is. And Q3 also will not toggle as it is. Now second clock pulse applied. Again Q1 toggles from 1 to 0. Toggle means 0 to 1, 1 to 0. Now since it is changing from 1 to 0, then Q2 will toggle. So Q2 will become 1. Earlier it was 0, now it is 1. Now what about Q3? Q3 will not toggle. When the Q3 will toggle? When Q2 is changing from 1 to 0, right? When Q2 is changing from 1 to 0, then only the negative edge occurs at the clock input, then it will toggle, right? So but here Q2 is changing from 0 to 1, so it will not toggle as it is. Whatever the previous state, it will maintain the same thing. Now third one you take, then again it will toggle 0 to 1, but 0 to 1 it will not contribute, it will not change the output of Q2. So Q3 output also will not be changed since Q2 is not changed. Next clock pulse applied. Now again it becomes 1 to 0. Since it became 1 to 0, this will trigger this. It will also become 1 to 0. Since Q2 is changing from 1 to 0, then Q3 also changes, right? Now it will become 0 to 1. Okay. Now fifth clock pulse. Again it is 0 to 1. 0 as it is. 1 as it is. Next sixth clock pulse. It will become 1 to 0. When it is 1 to 0, it will toggle 0 to 1, but 0 to 1 will not change the last one. And you apply seventh clock pulse, then it will become 0 to 1. This will not change. When you apply 8th clock pulse, it will become 1 to 0, and this will trigger this, it will become 1 to 0. This will trigger this, it will become 1 to 0. If you take Q3 as MSB and Q1 as LSB, for the states, if you write the decimal equivalents, state I can say decimal equivalent. If I write 0 0 means state 0, 0 0 1. Q3 is MSB, let us say. So it is 1, next one is 2, 3, 4, 5, 6, 7, then 0. Again, this from then onwards, for every clock pulse, for every 7, 8 clock pulses, the same pattern will repeat. If you see, nothing inputs we are giving. So based on how many clock pulses are applied, let us say this counter you're starting from 0 0 0. Initially, all flip-flops are reset. Counter is 0 0 0. Now based on the state, how many clock pulses are there, we can tell. So it can count up to 8 clock pulses, as I said. Let us say initially 0 0 0 is there. Now applied few clock pulses, you don't know how many applied. Now after some time, let us say you have the state here 1 0 1. That means state is 5, means we can say 5 clock pulses are applied at the input. Okay, this is how it works. Now this we can say up counter, because the states are going from 0 1 to up to 7. The counting is towards up, so we can say it is up counter. This we can say mod 8 up counter or 3-bit up counter. See, actually nothing inputs we are giving except clock pulse, nothing we are giving input. J and K we are giving only we are giving J and K input such that uh, they will change their states, toggle. Then only this kind of counter is possible. If they are not toggling, let us say J0, let us say J1 and K0 if you are giving. For example, instead of 1 and 1, your question, now I will answer your question. Instead of 1 and 1, let us say the first one I am giving J1 and K0, something like that I'm giving. Now what will happen, how many number of clock pulses you apply, you know, for J equal to 1, K equal to 0, always the output of flip-flop is 1, right? Always the output of flip-flop is 1. Okay, for J1, K0, you know, the flip-flop will set. Always output of flip-flop is 1. Always output of flip-flop is 1. It cannot change the output of next flip-flop, right? Because when the clock input is changing from high to low, then only the flip-flop will be triggered, right? You know, synchronous flip-flops are synchronous circuits. When the output will change, you have to apply the inputs, and when you apply the clock pulse, then only the output will change, right? Now let us say if you are giving, let us say J1 K0, so output is constantly 1, that means it's high, something like this. Always initial output 0, always output is 1. How many number of clock pulses you give, then there is no question of changing, triggering the next flip flop, right? You got it right? How many number of clock pulses you apply, Q1 always be 1. When Q1 is 1, Q1 is not changing, let's say Q2 always 0, because initially we're starting with 0 0 0. Then Q3 also always 0, whatever you give. Okay, is that okay? So when you are giving in toggle mode, then only the flip-flops outputs will change. Is that okay? Yes, understood. Yeah, fine, thank you. Now coming back to our question, yes. This is the question they have given. So a binary counter with synchronous clear inputs. Yeah. Now in this counter, let us say at some point of time, it's a 3-bit counter. Okay, it's a 3-bit counter. Now it can count from 0 to 2 cube minus 1, that is 0 to 7. It can count 8 clock pulses. Suppose if you want to prematurely terminate this, so that means this counter is going like this, starting from 0. 0 to 1 state it can go, then 1 to 2, like that, 2 to 3, like that it can go up to 7, then 7 to 0, it will go like this. Suppose if I want this state should be like this: 0 to 1, 1 to 2, 2 to 3, or 2 to 3, 3 to 4. After 4 I should get 0, I should not get 5. That means I want to change its modulus. Here it is a mod 8 counter, it can count from 0 to 7. That means 0 1 up to 7, then 0 1, like this. I want to make it as mod 5 counter. That means it should count from 0 to 5 minus 1, 0 to 4. That means 0 1 2 3 4, then 0 1 2 3. Okay. To make it like that, to prematurely terminate the counter, reset the counter, I should use some combinational circuit. Okay. And the out, I have to use some combination circuit, some gates, any kind of gates I can use, not only single gate, many gates. And for that entire combination circuit, your inputs can be the outputs of the flip-flops. Okay, we have outputs of the flip-flops. The inputs can be the output of the flip-flop, and the output will be connected to the clear or reset inputs of the flip-flops. Okay, just like in this question. So actually the counter, normally it counts, but here you see we are giving an extra XOR gate. Through XOR gate, for the XOR gate inputs are Q0 to Q3. And what will happen, what happened to some flip-flop when it is connected to the clear input, synchronous clear input. Now when you are activating the clear input, then what will happen, all the flip-flops will be reset, all the flip-flop outputs will be reset. You got it right? In the previous one only, whenever, let us say, I am connecting some combinational logic. Here I am telling some combinational circuit I am using. For this combinational circuit, this Q2, Q3, Q4 as inputs I am giving. Sorry, Q1, Q2, Q3. Inside the combinational logic, some logic gates are there. Now this output I'll give to the clear input or reset input. Clear input. Okay. Right, these are called asynchronous inputs. So what will happen when you're activating, when you're giving clear input, without, even though you don't apply inputs, you don't give the clock, but all of a sudden all the flip-flops will be cleared. You got it right? Let us say the combinational logic circuit output is, let us say, 0. When the output is 0, the clear input, active, low inputs, these are. So when the output is 0, all the flip-flops will be cleared. All the flip-flops will be cleared, then the output of all the Q1, Q2, Q3 all become 0. It is coming to the initial state. Okay. Now in this circuit, in the question, same thing is happening here. Now ideally, so for this binary counter, whenever you are applying clock pulse, the output should increase. Let us say you are starting Q3, Q2, Q1, Q0. Okay, you're starting from 0 0 0 0. Okay, initially you applied one clock pulse. What will happen? It will, binary counter means it will count in this from 0 to how many, 4 outputs are there. That means 4 flip-flops are being used, Q0, Q1, Q2, Q3. That means it can count from 0 to 2 power 4 minus 1. So it can count from 0 to 15. So binary counter means 0 1 2, it will follow that order. When you apply first clock pulse, then it will become this one. When you apply second clock pulse, then it will become this one, like this. Okay. When you apply third clock pulse, this one. Okay. But what we are doing here, it can go up to like this, up to when you apply the 14th clock pulse. 15th clock pulse, then it can go to 1 1 1 1. When you apply the 16th clock pulse, then it will become 0 0 0 0. This is the normal counting sequence for this counter. But extra some XOR gates combinational logic circuit is used. Now inputs for this combinational logic circuit are what? Input for this is Q3 and Q2 are given. So input for this is XOR gate is given, Q3 and Q2 is given. Now we know a two input XOR gate, that is, sorry, it's an XNOR gate. A XNOR B is what A bar B bar plus AB. Okay. Now for XNOR gate, when the output will be 1, now you can see here, you can see here the clear input is active low. That means whenever the clear input is 0, whenever the clear input 0, the entire counter will be reset, cleared. That means again it will go to 0 0 0 0 state. Okay. That means whenever the clear input is 0, the counter will be reset. Okay. Clear input is 0 means this you can say XNOR gate. XNOR gate output should be 0. When the XNOR gate output is 0, a two input XNOR gate, we know A and B are there. So A XNOR B, truth table you might have seen. So 0 0 0 1 1 0 1 1. Okay. So any when both inputs are either zeros or ones, then the output is 1, and one of the input is 1, then output is 0. This any one of the input to the XNOR gate, then output will become 0. Now that means either Q2 or Q3, whenever any one of Q2 or Q3 are zeros, 0 and 1 like that, then the output of the XNOR gate will be 0. Now the 0 is fed to the clear input of the this counter. Then all the flip-flops will be cleared. The counter will be cleared or reset. Now if you see this sequence, when fourth clock pulse is applied, what will happen? 0, 1, 0, 0. Whenever, see, for the first three clock pulses, first clock pulse, second clock pulse, third clock pulse, the output is what you see. Q2, Q3 are both at zeros. That means XNOR gate output will be 1 only. You can see for XNOR gate, when both inputs are zeros, then the output is 1. So I'm just writing the XNOR gate output also here. XNOR gate output for all these cases, output is 1 only. Now whenever the fourth clock pulse applied, then what will happen? Q2 is becoming 1, Q3 is 0. That means 1 of Q2, Q3. For this XNOR gate, one input is becoming 1. That means output will be, XNOR gate output will be 0. That means counter output will get something like this. 0 1 0 0. We are getting counter output. But immediately Q3 is 0, Q2 is 1 is going. Now when Q3, Q2, 1, the output of XNOR gate will be 0. That means it is connected to the clear input. So immediately this state will be cleared. It will not stay for long. Within fraction of time, this entire, all the flip-flops will be cleared. Why? Because for XNOR gate, for this XNOR gate, we are giving 0 1 input. Output of XNOR gate is 0. Now it is connected to clear bar input. So clear bar will be active, all the flip-flops will be clear. Okay, that means up to 3 it is counting normal sequence. When the fourth clock pulse is applied, it is immediately becoming 0. Okay, again 0, then it will go back to the initials. This circle it will follows. That means how many states it's counting? 0 state it's counting. one state, two state, three state. Whenever it is coming to fourth state, that is not permanent state. Within no time, it is going to again zero. That means 0 to 3 only it is counting. So 0, 1, 2, 3. From 3 again it is going to 0. That means it is counting from 0 to 4. That means it is mod 4 counter. Okay. It is a mod 4 counter. So option B is the correct answer. Is that clear? Am I clear?
Sir, what is the difference between synchronous clear input and asynchronous clear input?
Synchronous clear input means
Are they different?
see actually generally taking these inputs clear and reset they are like asynchronous only. That means it doesn't matter whether you apply clock or not. With irrespective of clock pulse, the output of the flip flops will change. Okay, that means see generally let us say we have clock pulse negative edge triggered flip flop only you consider. At the negative edge of the clock, based on the inputs, the output, the state will change, right? Generally for a flip flop at the negative edge of the clock, based on flip flop inputs, the output will change. Let us say for JK flip flop, now both the inputs are 1. Now at the negative edge, if based on previous input, previous state is 0, now it will become 1. Previous state is 1, now it will become 0. Okay, that means whenever for a flip flop, whenever you are applying the inputs will not affect till the clock pulse applied. So you have applied input, but you have not applied clock pulse. That means input will not have any effect on the output, on the state. Only when the negative edge comes, then only. Now for the clear and reset inputs, for flip-flop, you know, right, clear and reset inputs will be there. Clear means whenever you apply the clear input, sorry, clear or reset both are same, and also set input also will be there. Okay, now let us say clear or reset input. Whenever you are applying clear input, irrespective of the flip-flop inputs, whatever may be the flip-flop inputs doesn't matter, and whatever may be the clock, it can change. Okay, that means somewhere here you applied the clear input. That means negative edge trigger is not there, but still this will change the state of the flip-flop. Somewhere here you applied here, till here the output of flip-flop is 0, sorry 1, let us say. Now suddenly here you applied the asynchronous input, then the flip-flop output will uh, change from 1 to 0. You no need to wait till that clock comes. That is actually how the asynchronous inputs works, set and reset inputs. Okay, but here it is mentioned synchronous clear input. Maybe they mean whenever you apply clock, then the output will change. That means here their meaning is maybe when fourth clock pulse is applied, then immediately the output will become 0100 whenever the fourth clock pulse applied. When 0100, immediately the flip flop, sorry, the XOR gate output will become 0, and it will clear the outputs of flip flop. That means whenever the clock applied, 0100 will come, this entire cycle will take place, and output will get 0000. Here their meaning is that one synchronous clear input means uh, with application of clock the output of counter will change to 0100, then immediately all the flip flops will be set, sorry, reset, then the state is 000. That means you will consider when fourth clock pulse is applied, directly we will say like 000 is the output, not this intermediate one we won't consider. That is the meaning. Okay, but generally for flip flops, generally the clear A reset input is asynchronous one only, irrespective of clock. Is that okay?
Sir, I checked with that answer key from 2015.
Okay.
It was option C.
Okay, it's mod 5 counter.
So it is mod 5 counter for synchronous clear input and mod 4 for asynchronous.
Okay, okay, okay. Fine, maybe my understanding may be wrong for this. Maybe synchronous clear input means when the fifth clock pulse comes, then I think it will. Okay, maybe that one, I guess. So if it is asynchronous clear input means irrespective of clock input, the output of the flip-flops will change. Synchronous means maybe whenever the next clock pulse comes, let us say negative edge triggered, at that only it the outputs will be cleared. Maybe after application of fourth clock pulse, the outputs are 0, 1, 0, 0. Okay. Now for this XOR gate, XNOR gate, no need of giving any clock input. So output of XNOR gate is 0. Since they said it is synchronous, whenever next negative edge trigger comes, then only the flip-flops will be cleared. That means uh, when the fifth one comes, then only the flip-flops will be cleared. Maybe then the output. Okay, got it, got it. Here they have not given the entire circuit, right? Maybe we in this it can be something like this. Sorry for this. I did not focus much on that. So let us say this is clear inputs for the flip-flops. Now, suppose now XOR gate only. Let us say you take this is the counters like Q0, Q1, Q2, Q3. Now that XNOR gate only. I'm just drawing this XNOR gate only. This one. For this, all Q1, Q2, Q3, Q4 are connected. Suppose if we are connecting directly like this. Now I got the difference. If we directly connect this, now whenever the output of this becomes 0, then all flip-flops will be cleared irrespective of the clock pulse. Now this is asynchronous. Okay. Now instead of directly giving like this from XNOR gate, let us say we are like kept some combination circuit. One input to the combination circuit is clock, and another input, sorry, this output, and also another input is clock. Okay, clock is connected here, and also the clock is connected here. Through clock, it if it is given. Okay. Is that okay? Now, whenever the clock comes, then only the output will change through some AND gate or OR gate like that. Okay. Is that okay? So in this question, if it is asynchronous clear input means then it's a mod 4 counter. It's synchronous clear input means after fourth clock pulse output becomes 0, 1, 0, 0. Whenever the next clock pulse comes, then only all the flip-flop outputs will be cleared. So in this case, so if it is synchronous one, output of XOR gate after fourth clock pulse, output of XOR gate is 0. but still they cannot clear the this one. So fifth clock pulse should come, then only this will be clear. The clear inputs will be effective whenever the next clock pulse comes. Is that okay?
Yes, sir.
Fine.
Mod 4 or mod 5?
So this is for asynchronous clear inputs. It is mod 4 counter. Synchronous clear inputs. It is mod 5 counter. Okay. For synchronous clear inputs, it is mod 5 counter. The next clock pulse should come, then only it can clear the outputs. Okay.
So it should be only XOR gate.
But no. Any other gate you can use. Any gate. Any gate you can use, not only XOR gate. Here, if it is XOR gate is used, this one. Suppose if it use NAND gate instead of XOR gate, let us say we use some NAND gate here. Let us say NAND gate we are using. Now, not NAND gate. Any gate we can use. I mean, different ways. This is one way of connecting Q2, Q3, Q4, like that. Different ways of connecting also there. So NAND gate also gives, I think, the same thing. NAND gate means output will be 0 when both the inputs are 0. NAND gate means, so based on the gate, whatever combination circuit you use, so based on that, it will be like mod 3 counter, mod 5 counter, mod 7 counter, like that. Okay, based on the combination circuit that we use. Not only this, any gate you can use, but based on that, it will change. If XNOR gate you have used it like this, maybe NOR gate if you use NOR gate or NAND gate, any gate, just we have to analyze in the same way. Okay.
Sir, you are saying asynchronous clear input is directly given.
Okay.
And synchronous clear input is given through a clock.
Yes. If it is like instead of directly representing the counter like this, so elaborately inside flip flops, everything are there. Then through clock also will be some arrangement will be there. Then only whenever the clock pulse is there, then only the input should be affected in such a way that maybe an AND gate will be there. Okay, AND gate or NAND gate, something whatever like suitable gate will be there, so that whenever the clock pulse is applied, then only these inputs will be cleared or reset.
Means it will count the last clock also, after which it is cleared.
Actually, see, as I said for the previous one, after fourth clock pulse, the output of this is what 0, but still this 0 cannot affect the inputs. Only when you apply the clock pulse, then only this 0 will be transmitted here. Okay. Some combinational logic will be there, the suitable gate or combination of gates. Okay.
Okay, sir.
If you draw the entire circuit inside, I mean, something like that will be there. You can check maybe in your textbooks, that might be also there. Fine. We will move on to the next question. Okay, this is the question that was given GATE 2015 ECE set to for 2 marks. The question reads as follows. The question is uh, a 1 to 8 demultiplexer with the data input D in and address inputs S0, S1, S2, S0 as the LSB and Y0 to Y7 as the 8 demultiplexed outputs is to be designed using two 2 to 4 decoders. Okay, with enable input also there as shown in the figure. So S0, so D in S0, S1, S2 are to be connected to PQRS. Okay, so then but not necessarily in the same order, the respective input connections to PQRS. That means what the question means is there is some circuit is given, PQRS as the inputs and outputs are given. The circuit is designed with two decoders, 2 to 4 decoders. Now this entire thing should work like a 1 to 8 demultiplexer. That means 1 to 8 demultiplexer means one input will be there. So data input, only one input will be there and many outputs will be there. Y0, Y1, Y2, 7. 7 outputs will be there. And any one of the output will be active based on the input. That means, sorry, so based we will have some selection lines for this S2, S1, S0. So based on the selection lines, the data at the input will go to the any one of the outputs. Let's say selection lines are 0, 0, 1. Then data, whatever data present, the input line D in will be connected to Y1 output. Okay, this is 1 to 8 demux. Okay, now we need to connect this PQRS. That means for this 1 to 8 1 to 8 demux, it will have S2, S1, S0 are the selection lines and D in is the input. Now this entire setup should work as a 1 to 8 demultiplexer. Then how we have to connect PQRS? That means we need to connect D in, S2, S1, S0 data input and selection lines to this such that the entire setup should work as a uh, demultiplexer. Okay. Now before that we will try to understand about a decoder. Let us say if it consider 2 to 4 decoder, so it will have two binary inputs. Let us say two binary inputs, let us say A0 and A1. Sorry, A1, A0. And we will have some outputs Y0, Y1, Y2, Y3. Now based on the inputs, binary inputs, any one of the output will be active. If it is active high outputs means outputs based on inputs A10, A20, its decimal equivalent is 1. Y1 will be active high and remaining will be zeros. Any one of the output will be active. This is for active high. Suppose the inputs are 1, 1. Then all the input outputs are 0 except Y3 is 1. This is for active high outputs. Okay. Now extra, so suppose if we have active low outputs, means A1, A0 are the inputs. Active low output means there will be a bubble or not inverter followed by the output. That means initially all outputs are 1. Based on whatever input you apply, let us say 1, 0 input I am applying. Based on that, any one of the outputs will be active. 0 means active here. Okay, all will be 1 except that. So decimal equivalent of 10 is 2. So y2 will be active. This is active low output. So the decoders given in our example are active low outputs. And there is something called enable input, chip enable, decoder enable. The decoder will be enabled only this enable you have to apply. Suppose if enable is 0, I'm giving. If enable is 0, then irrespective of what input you will give, the decoder is inactive. Okay. So even though you gave inputs 1 0, the decoder is inactive. Okay. When you make the enable active, that means here active high enable, let us say. When you give enable is 1, then only the decoder out will become active. This is active high enable, but in our example active low enable is given. So that means enable bar. That means what? There will be a bubble like this. A directly enable bar means whenever the enable bar is 0, then decoder is active. For 1, inactive. Decoder is inactive, not enabled. Then only it is enabled for 0. Okay. Now if you see here, in this example, if you see here, A0 and A1, this R and S are connected to A0 and A1. Okay. Of the both the decoders. And this Q, if you see, now Q, if you see, for first decoder through an OR gate is directly connected. For the second decoder to an inverter, then OR gate is connected. Okay. If you see here, this we can say selection line to S2, because you can see if let us say Q is S2, if Q is S2, let us say I am consider Q is S2. Now let us say if S2 is 1, or let us say S2 is 0, then output of this OR gate is 0 and output to the next OR gate is 1, because it is going to an inverter. Okay. Now output of this OR gate is 1. Now this 1 is connected to enable input. That means this entire decoder is not enabled at all, because it is active low inputs, right? So for the first decoder, now based on p value, let us say p is 0, for example, then it is going here, then the first decoder will be active. So what we can understand is S2 selects the any one of the decoders. Okay, S2 selects any one of the decoders. Suppose S2 is 1 if I am taking. S2 is 1 if I am taking. So irrespective of P, output of this is P plus 1, always 1. Now the first decoder will not be enabled. The second decoder only will be enabled, because the output of this NOT gate is 0. Here based on P, output of this is P. Sorry. Yeah. That means S2 works as, now S2 is 0, the first decoder will be enabled. That means output 0 to 3, any one of 0 to 3 can be active. If S2 is 1, the second decoder will be enabled. Any outputs from 4 to 7, anything can be active. That means clearly we can say S2 is connected to Q. Okay, one of the selection lines. Now what about R and S? R and S, that is common to A1 and A0. Okay. Now A1 we can say S1. So that means A naught. A naught is connected to R, A1 is connected to S. That means R I can say S naught and S I can say S1. Okay, so R should be S naught and S should be S1. And what else the left? Data. Data input should be connected to P. Okay, now just let us cross check whether it is correct or not. Now let us say Q input, that is I am considering as S2, I am giving 0, Q input is 0, then the lower flip decoder is inactive and the upper decoder is active. Lower flip flop is inactive means all outputs are 1 1 1 1. Okay, now let us say data P is the data. Now let us say R and S I am giving 0 and 1. R and S 0 and 1. Now R0 S1 means here 1A naught and 1A1 becomes 0 and 1. For the first decoder 0 and 1 are the inputs. Based on that which one should be active, Y2 should be active and all other will be inactive. Okay, Y2 should be active and all other will be inactive. Now what will go? Let us say if P I am giving 0, that means here the output of the first OR gate, if you see here, S2 plus S2, since I am giving 0 plus P, that means P we are giving at the enable. If P is 0, then enable input 0 we are giving, output we are getting 0, Y2 we are getting 0. That means whatever data we are giving at P input, the same data we are getting at the output. Now P equal to 1 I am giving, let us say. P1 means the output of this OR gate will become 1. So 1 means the upper decoder also like inactive only. That means inactive means Y2 also 1. So we can say for P1, Y2 also 1. You got it right? Now let us say P0 only. Let us say I am considering P0 only. For S2 0, Y2 will become 0. Now let us say S2 1 I am giving. So P0 I am giving and S2 1 I am giving. Now when S2 is 1, this one, then what will happen? Upper decoder will be inactive, lower decoder will be active. Now R and S are ones. So R and S are 1 means this will be active. So here you will get 0. That means 1 0 1. So 1 0 1. So that is, yeah, this is, I said S naught, this is S1. So S2, S1, S naught, 1 1 0, right? So which one? Y6 is active. So from this you can say P is D in. So P is D in, Q is S2 and uh, R is S naught and S is S1. So option D, this is the answer. Is that okay? I think we're running out of time. Do you have any doubts from this? I thought of covering few more questions, but anyway, any doubts from this? If you have doubts, you can ask. Otherwise, you can join the other session. Fine. Thank you. Thank you, everyone. We'll stop here.